Hello everyone. So in the lecture series of basics of software defined radios and practical applications, today we are covering power amplifiers, which are the main source of the nonlinear distortion in transmitted signals. Till last lecture we have covered the nonlinearity distortion due to the single band and single tone and two tone signals. So we have discussed that in the modern scenario mostly our signals are multi carrier signals. So in that case our criteria of judging the distortion changes a little bit. So in this left hand side figure we can see a 3 carrier WCDMA signal. If you see, it has a carrier frequency of 1.96 gigahertz, then it has bands which are 5 megahertz away from the center on the both side, and at the center frequency there is no carrier. So it is basically 2 carrier signal, and both the carriers are broadband and they have the bandwidth of 5 megahertz almost. So in this case we are showing the input signal, which is shown by the green signal, and then when we drive this power amplifier to high power, then we have the power output saturation. So the black color signal is the output of the power amplifier. So this distortion is appearing in the in band as well as adjacent band. In frequency domain it is easier to visualize the adjacent band distortion, and we can also see if we are driving our power amplifier at a back off, it means we are giving less power, which is shown by this red curve and that blue and the yellow curve also, then the distortion goes down as we keep increasing the output back off of the power. So in this case, when we are using multi-carrier or wideband signals, our distortion is not measured by signal to noise ratio, but similar kind of metric is used for that, which is called adjacent channel power ratio. So adjacent channel power ratio is the ratio of the powers in the in-band signal and the adjacent channel frequency. So it is also called adjacent channel leakage ratio. If we see here that B is the band where we are having the signal. So we can choose either this carrier or this carrier, or we can take this carrier and take the average of these two carriers. So we are doing the integration of all this band. So average power of this signal is lying here, and when we do the integration of our whole band, then we get the power which is inside this complete signal. Similarly, at the adjacent channel we choose a offset which is given by this blue arrow, and it is called the power offset, and normally whenever we are giving ACPR which is a particular value at a particular spot, then we always define this offset, that at this offset we are measuring this ACPR. At this particular offset, around that offset we take a particular bandwidth which is represented by Bx here, and then we integrate the power in the channel for that particular band. So it will be the ratio of the power in this band with respect to the ratio of the power in this particular band. So as you can see, this black one will have a higher noise, so it will have lower ACPR, the red one will have much higher ACPR, and the blue and the green, they will be having much more higher ACPR here. So this was the ACPR or the leakage ratio at a particular spot. Now when we are dealing with the dynamic range of the multi-carrier or wideband signals, you will see in the literature people talking about the total ACPR. When we are talking about total ACPR, then it includes both the adjacent channels, means you will have low side or upper side. So in this case lower side will be this below the carrier frequency, upper side will be above the carrier frequency, this direction. So we capture our power at this location as well as at the upper side location, and then we add them together and we show it with respect to our in-band power, the output power at this particular band. Similarly, sometimes we are interested in showing our ACPR power at particular side band, maybe lower side or upper side, because they are interfering with the particular channel. So, we must understand this thing, that whenever we are using power amplifier and these are the allocated frequency to us where our power amplifier is working, the nearby frequencies might be allocated to some other subscriber. In that case, if these distortion components are appearing there, then they will interfere with the signal which that particular subscriber want to send. So, of course, they are undesirable and we have to control them. Now, another nonlinearity specification due to power amplifier is EVM. It is called error vector magnitude. So, it is represented in terms of the deviation in the constellation diagram. So, if you look at this 16 coulomb signal in the constellation diagram form, we have our I phase and the Q phase, and this is the original location of the symbol. But because of the distortion, the symbol is not lying at its original location, and after demodulation it goes to some other point. So, this is the actual symbol and this is the measured symbol or ideal symbol, I would say. So, the distance between these two, ideal symbol and the actual symbol, this is what we called error vector. So, this error vector is what we measure for all the symbols, and then we take root mean square for all those values, and it is called error vector magnitude. So, in this formulation, our I2 is a particular position of the actual symbol, and this I naught is denoting our actual symbol. So, I2 minus I1 and Q2 minus Q naught, they are giving the distance in the I direction and the Q direction, and we calculate the distance between these two error forms, and then we take root of this value and we normalize with the actual amplitude, absolute amplitude of that symbol, which was originally this one. So, this is the definition, and how do we apply it? So, EVM calculation for OFDM based signals is given by this formula. In this formula, LP is representing the packets, number of packets. This NC is number of carriers on which we have mapped all our symbols. So, if we are covering all these carriers, then our all of the symbols are being taken care of. Now, one frame contains this many packets, and if we have enough frames, then we will have so many I and Q position in the constellation diagram for all this data. So, this is for a particular OFDM based signal. We calculate for each carrier, then how many carriers were there originally in one packet. We repeat that for all the packets, and then how many packets were there in a particular frame. We take the root mean square of all that value, and then we normalize it with all number of frames to have one particular value in the RMS. Now, in some of the literature, if you come across the term receiver constellation error, it also denotes to this particular definition. It is again the EVM. Now, if I multiply this with 100, we can give the percentage EVM, which is achieved by multiplying this EVM RMS by 100 directly. So, that was in the constellation domain. Once we have our signal in digital domain, in the baseband domain, but it is not in the constellation form. Some of the literature, they also give the definition of EVM in this term, where YIN is the original signal and YIN is the original symbol which we transmitted, and YN is the symbol which we actually finally received. So, we take the error between these two symbols and take the absolute of that, and then we square it, sum all the data which we have, and then we take the root mean square of its normalized value. So, we sum all the data which we actually transmitted, and we sum square of all the errors, and this is also denoted as EVM in some of the literature. Now, there is a term NMSE, the full form is normalized mean square error. It is simply the squaring of the EVM. So, basically when we are dealing with the baseband data, before we demodulate it into constellation form, in the baseband we have a data in the discrete time domain. So, after ADC, we have our data which will look something like that for the I as well as Q. So, we have both of these data and they are in the discrete domain, in the N domain, and X can be I or Q. So, then we can actually measure these values, we can actually read these values, we have availability to this value. Just before we do the root trace cosine filtering again, just before that we capture this data, it is in a continuously increasing decreasing form, and then we do the I n plus j q n in the digital domain. So, the data which we transmitted was this one, or yi ideal y, and data which we received actual y is I dash n plus j q dash n, and we are comparing these two values. So, basically we are just normalizing the error between that, and we use this value a lot, especially when we are talking about the power amplifier and transmitter output. Now, what is the relation between these values with the SNR? This SNR should be actually dynamic range, and the relation is given as 10 log 10 1 upon EVM square. So, of course, if you look at the definition of NMSC, we are dividing the power, the summation of the each symbol power by the error of this term. So, of course, if we invert this and take 10 log 10, we will get signal to error ratio. So, if that distortion power is very high, in this case, when the distortion power was very high and we are getting this kind of components, it is overriding all the noises because of the phase noise, quantization noise, temperature noise, and then it will be the defining factor here. It will give you the ACPR or the dynamic range of the signal at the PA output. So, therefore, our SNR which should be actually ACPR or the dynamic range is the inverse of this NMSC, and if we take 10 log 10 we get the dB of this particular value. Now, another one of the nonlinearity specification is given in terms of AM/PM conversion and AM/PM conversion of the power amplifier. So, what is AM/AM and AM/PM conversion? Whenever So, whenever we are applying any data to PA and we are capturing some data, I am showing in discrete domain, digital domain basically, but power amplifier works in RF domain, right, and after that mostly RF analog domain. But what I want to represent here is the data which we captured in the digital domain eventually. So, if input data was xn, which has the amplitude A n sine if this was the input signal, then our output signal at the power amplifier is not exactly the replica of the input signal, right. It becomes it has an amplitude which is a function of the amplitude of the input signal, and it has a phase which is also a function of the amplitude of the input signal. So, when we want to observe the performance of any power amplifier, we want to have a look at these two factors, because these are the two factors which are differentiating it with respect to the input signal. So, of course, it will have a gain, but it will also have some kind of distortion. So, ideally when you are sending a input signal, the output signal gain should be a straight line. Why? Because for a particular input you should have a particular amplified output. So, when we have a look at this first diagram which is showing the AM/AM or amplitude to amplitude modulation, then we are increasing the input power, and we can see that amplitude to amplitude modulation, which is basically simply R AN upon AN. This is what we call AMM modulation. If you look at this, what is this? This is basically the amplitude of the second waveform divided by amplitude of the first waveform, amplitude of the output divided by amplitude of the input, and by definition it is what? Simply gain. So, this AMM, whenever we are talking about AMM, it is simply the gain of the power amplifier. So, when we look at this diagram, the gain was straight when the input power was very small. So, this was the linear region for power amplifier. After that, when we keep increasing the input power, the output power becomes nonlinear, it becomes saturated. In this particular case, it is a power amplifier which has this particular nonlinearity profile. So, instead of giving a straight line in the gain, it is having this kind of nonlinear profile after let us say input power of minus 25 dBm. Similarly, AM/PM is the phase modulation because of the amplitude. So, here we are basically simply plotting the output phase minus input phase with respect to input power. So, AMM was the gain and AM/PM is basically this phi AN minus input phase. So, for example, we would have initial phase like this, then we will say this is the AM/PM, and we plot it with respect to input power, and that is how it is called with respect to the amplitude of the input signal. So, if you look at in this diagram also, we can see this phase is almost constant till minus 20 dBm. After that, there is a great fluctuation and nonlinearity comes into picture and it becomes compressed. Now, this profile of the gain and phase distortion and modulations, they are typical of any particular power amplifier. So, the figure here shown is for a particular Dorothy power amplifier, and for different devices, different classes of power amplifier, we will have different kind of profiles. So, what are those classes of the power amplifier basically? Whenever we are selecting any power amplifier, we look for 4 things: gain, the output power it can provide, efficiency of the power amplifier, and linearity it can provide. Means after how much input power it will become saturated. If it can become saturated after a larger distance of the larger input power, then it is good for us because it will have lower distortion. Now, typically a power amplifier takes RF input power, which is the signal which we want to amplify. Apart from that, it takes DC power from some other source. Some DC supply is always connected there, and by using the power of this DC supply, it provides the power to this RF input power, and it is having this high output power which is called RF output power in this range of the frequency, which is the RF frequency range. Now, if you look at this diagram, we are showing different classes of power amplifier. Class A amplifier is considered most linear amplifier. If we see, it has very high gain and it has good output power, but it has very small percentage of efficiency. So, it has very small efficiency, it converts very small portion of this power to output power. So, it requires lots of DC power. Now, if we do the change our conduction angle, we reach class AB. Class AB power has much higher efficiency as compared to class A, but because of that we have to choose between A and B, then our output power and gain are less than the class A amplifier. Class B amplifier becomes even more non-linear there, and it has lower gain and output power as compared to class AB. Efficiency is higher as compared to the class AB. Now, class C amplifier is having the higher efficiency with respect to B, but it has lower output power because of its profile and it has lower gain. Now, this kind of amplifiers are called continuous mode amplifier, because you are seeing that they have some conduction angle and they send the original signal into some form or other. Now apart from this continuous mode power amplifiers, there are some other amplifiers which we call switch mode amplifiers. So they send the data in the form of switching operation. So the distortion caused by this kind of amplifiers are separately, and they require separate kind of linearization methods. So these two categories are there, and we are mostly focusing on these for the time being, and class B and class B and class AB are the mostly used power amplifiers in a transmitter. Now once we have the idea of the classes, based on our requirement we can choose any of these amplifiers and use them. Now let us have a look at some of the basic definitions which are relevant to the power amplifier. For example, whenever we are calculating the signal power at the input and output, we will be provided our V and I. If we know the exact value in the complex form of that V and I, then we can do the multiplication of V input and conjugate of the I input. In the data sheets you will be provided RMS values. In that case we do not need this half value, we can simply multiply them, because it will become V upon root 2 into I upon root 2, and V upon root 2 is the RMS value, so you can directly use that value. Now when we are writing that frequency is in the range of F low to F high, then we are just giving the range of the in band power. So most of the power is concentrated in the in band. The distortion components mostly go out there, right. So in case of the input signal, mostly all the power is in the in band. In the output power, if we do not have any leakage into the adjacent channels, in that case the similar kind of calculation can be applied for the output power calculation, and it will denote our band of interest. But in some of the cases, some of this power is not part of that band, and we have to take that into account. Now apart from this power, input power and output power, there is something called saturation power. So what is the saturation power? If we keep increasing the power of the input signal, then our output power will become saturated. This is what we had seen. So that power where this saturation starts, it called the saturation power, and of course it then cannot go to the infinity. At some particular input power it will simply burn. So this is the power after which it start losing its linearity. So there are some definition for that which we will review here. Now the calculations of the power. Normally when you will see any data sheet commercial components you want to purchase, then they can give you the value in the watts as well as they can give you value in the dBm. So if your power in the watts is given by capital P, then if you convert it back into milliwatt first and then you calculate its logarithmic power, then it is called dBm power. So this is the calculation, and we have covered it and used it before also, that 10 log 10 of the original power plus 30 will give you the dBm power, or if you already have the dB power, then dB power plus 30 will give you the dBm power. Similarly in the milliwatt you can calculate your power by using this calculation, and 10 to the power P dBm divided by 10 will give you P milliwatt power. So this definition you have to swap sometimes, many times, in fact, because once you want to convert back from power to voltage, you always have to go to this milliwatt or watt calculation, so that you can apply V square upon 2R formula and get your voltage levels mostly. So power gain. Power gain as I am showing in this diagram is similar to our AM/AM diagram which I had shown earlier. It is the ratio of output power divided by input power in the band of interest. What is small signal gain? Yeah, this term is also very common to appear in the literature. A small signal is the gain when your P input is 0. Again, we are showing limit of the input power going to 0. Normally we have very small level of power, it does not go to 0 because we have noise in the system. So, as we can see in this diagram, the system was linear for some time and after that it becomes non-linear. So, this range for this for which it is linear, it is the this gain here is the small signal gain. So, in this case we can see that our small signal gain is almost 0 for this diagram, and this scatter point around this, they are because of the two factors. One of them is noise, which appears a lot in the low input power level. Another point which we come across in the power amplifier is memory effect. Memory effect comes into picture because of the heating of the devices. Moreover, the energy storing components in the power amplifier like inductor and capacitors, sometimes to block the DC we have to use capacitor. This kind of elements, they store the energy and then they relieve according to their nature, according to their time constant. So, when that happens, then the output signal is not only the function of input signal, but the dissipated signal from the previous cycle is also getting mixed. So, Yn, which we are giving as a function of Xn, is not exactly Xn, it is a function of Xn, Xn minus 1, Xn minus 2 and so on. This M is called memory depth. So, by making this relation, by choosing the particular memory depth, we are able to find a proper relation between input and output, and this diagram shows the data of the practical signal. So, we are able to see this memory effect a lot, and instead of seeing one straight line showing this graph, we are seeing group of datas appearing around that normalized value. So, if we take the average of all this data and then we plot them, then we will achieve our memoryless profile of the power amplifier, nonlinear amplifier profile. Now, continuing with our definitions, earlier we have covered 1 dB compression point. 1 dB compression point is the point or input power for which the output power deviates from its original path by 1 dB. Now, because we are talking about the power amplifier, we are mostly interested in the output, not the input. So, we refer everything at the output of the power amplifier. So, whenever you are reading data sheets, most of the time you will see the output of everything, P1 dB output power. So, how do we calculate this output power of the P1 dB? Now, normally we have this relation between gain and the power. So, gain is basically V2 upon V1, right, and in terms of sorry, not the V2 upon V1, it will be actually V2 upon P1. In the sense of power we talk whenever we are talking about the amplifier. So, when this happens, we have our gain there, then we can say that we want to make a relation between input and output, then P2 or P out will be G times P input. If it is linear, they are simply watts and the gain, or if they are in dB, then because logarithmic expression is log A plus log B. So, we can simply give it in terms of G dB plus P in dB. So, both are logarithmic and they are in the summation. So, when we are dealing the logarithmic scale, the output power is simply the gain plus input power. Now, it might seem to us that we can simply get our output point of the 1 dB compression by adding the gain with the input power of the 1 dB, but that will not be true because our data has been compressed by 1 dB. So, the relation becomes output power is equal to input power plus the gain at the small signal scale minus 1. Now, this small signal scale is the gain which was proposed for the linear range. So, that is why we are deviating from that gain by 1 dB and we apply that formula to calculate our output power at 1 dB compression point. So, this is an important point because normally it seems that we can simply add the gain to the input power. It will not be the case when we are calculating the 1 dB compression point. Now, let us have a discussion on the output power back off. We have discussed that when we keep increasing our input power, our amplifier becomes saturated. If we drive our amplifier at some distance from some power previous to the input power, then we have a chance of getting lesser distortion. This is what we call output power back off, and I had shown you the figure when we can see the distortion level was less. So, it is interesting to note the C by IMD, this is third order intermodulation for a power at the some particular output power back off. So, if you remember our original discussion from the last lecture, the C by I ratio in dBc is actually twice of IP3 out minus P out dBm, and you also remember that our third order intercept point and the signal power has this relation with the IMD term, and we have gotten this expression for the two tone case. So, that is why we are showing it 2 omega 1 minus omega 2, it is the IMD3 component again. So, this IMD3 component is equivalent to C by IMD term here. So, IMD component can be given by 3 times the input signal power at the main frequency minus twice of IP3, third order intercept point. So, from that we can actually calculate our C by I, because C by I is given by this formula. Then what we can do, we can eliminate this IP3 from this formula. So, what will become of this formula? So, C by I, which is C by IMD3 basically, it is given by twice of IP third order intercept IP3 minus your output power in dBm. So, this was the original expression given there. Now, if we put our value of SSPA calculation, we have given a rule of thumb that P1 dB will be equal to IP3 minus 10. So, basically we can say IP3 will be 10 plus P1 dB. So, now if we have a look at this point, this P1 dB is the point where saturation starts, and saturation has already occurred. Because of this, the power has been dropped by 1 dB. So, we are talking about the current power which is subtracted from the saturation power. So, this is what will give us the output power back off. So, this distance is the output power back off from P1 dB point. So, it will become 20 plus 2 output power back off. So, if you understand this point, if it was the input power and it was the saturation curve for the amplifier, and it was, let us say P1 dB point here, and we have subtracted OPBO from here and we reached our original power, which was this power. So, this is what we are representing here, output power back off, and because of that, what will be our IMD, the carrier to IMD3 ratio is given by this formula, which is 20 plus 2 times OPBO. So, if we know the output power back off, we can simply have some estimate of the carrier to third order intermode by using this formula. So, in the next lecture we will continue with this specification, and we will see how we can actually apply a commercial data sheet to choose any particular power amplifier for our applications. Thank you.